You to picture the absolute cutting edge of the global AI race.
Right.
When most of us think about the primary bottleneck that's holding back artificial intelligence, our minds immediately go to silicon.
Yeah, we usually imagine like a massive shortage of highly advanced GPUs or, maybe a lack of complex coding algorithms coming out of those pristine laboratories in Silicon Valley.
Exactly. I mean, it is the most common assumption out there. We've basically been conditioned to think of the tech industry purely in terms of processing power and software
We
engineering.
really have. That's the narrative.
But then you look at a recent admission from Microsoft CEO Satya Nadella,
Right.
and it completely shatters that assumption.
Oh, absolutely.
Yeah.
He essentially realized that they're fighting the wrong war.
Right. His phrasing was incredibly blunt.
Mm-hmm.
He basically said, the real problem is not GPUs, it's power.
Yeah.
We have GPUs, but nowhere to plug them in.
Which is just a stunning admission. I mean, that statement fundamentally flips the script on what the actual limitation of artificial intelligence is right now.
Oh, it really does.
It's an acknowledgement that the bottleneck isn't digital anymore, it's physical.
And that physical bottleneck is driving this massive geopolitical and industrial shift. The world's biggest tech giants, Google, Amazon, Microsoft, Meta,
All of them.
but then realizing they can't rely on Silicon Valley to save the AI revolution. Instead, they're looking across the Pacific, and they are lining up in South Korea.
The scale of the capital moving over there is it's difficult to comprehend.
Yeah.
Big tech is projecting a staggering $650 billion spend on data centers in the year 2026 alone.
That is roughly 900 trillion won.
Right. So the true protagonist of this next era isn't a software developer or, a chip designer. It is whoever achieves total energy infrastructure dominance.
Today, we are going to explore how one country quietly acquired the entire industrial stack required to power the AI future.
It's a fascinating playbook.
But before we get to South Korea's playbook, we really need to understand the mechanics of why tech giants are in such a panic over electricity in the first place. I mean, we've had data centers for decades.
Sure.
Why is AI suddenly breaking the grid?
Well, it comes down to the sheer computational physics of a large language model. Think about what happens when you do a standard Google search.
Okay.
The servers are basically just acting as a digital filing cabinet. You type a word, the server retrieves a pre-indexed link and sends it back.
So it takes a tiny fraction of electricity.
Exactly. But a single query on ChatGPT, that uses 10 times more power than that standard search.
10 times the power. Just answer one prompt.
Because it's not retrieving a static file. It is generating entirely new text by calculating complex probabilities across billions of parameters in real time.
Wow.
It's doing massive matrix multiplications for every single word it outputs. And the trajectory of this is what has big tech so terrified.
Right, because it's scaling up.
Exactly. The energy data shows that GPT-5 consumes 9 times more electricity than GPT-4. As the models get smarter and more capable, they become exponentially more power hungry.
When you multiply that by billions of queries every single day, the scale becomes almost unmanageable.
It does.
I was reading a breakdown of the energy usage in the sources, and training a top-tier AI model just once takes as much electricity as 120 American households use in an entire year.
Which is exactly why the infrastructure lag in the United States has escalated into a full-blown crisis. By 2030, data centers are estimated to consume 17% of all electricity generated in the U.S.
That's incredible.
And by 2035, the demand from these centers will hit 106 gigawatts.
Wait, 106 gigawatts?
Yeah. To put that in perspective, that is nearly twice the annual power usage of the entire country of South Korea.
And the American grid they are trying to pull this power from is largely an aging patchwork. I mean, most of it was built in the 1960s and 70s. It's like big tech bought a fleet of million-dollar Ferraris. Those are the GPUs, only to realize the entire country is running out of gas stations.
That's a perfect way to put it. And building new power plants in the U.S. is basically a regulatory marathon.
Yeah, NVIDIA's Jensen Huang recently pointed out a brutal contrast on this. He noted that it takes 3 years just to get the permits approved for a data center in the U.S.
Right.
Whereas China can literally build a hospital over a single weekend. The U.S. is fundamentally losing the infrastructure speed war.
So if you are Microsoft or Amazon and the national grid can't handle your massive new load, you are left with only one option.
You have to secure your own power generation.
Exactly.
Yeah.
You literally have to build your own power plants to run your data centers. And this is where we see South Korea's heavy industry step into the spotlight.
So let's look at the first piece of this puzzle, which is gas turbines.
Right. Gas turbines are essentially the workhorses of modern power generation. You burn natural gas, the expansion of the superheated gases spins a massive turbine, and that rotational energy is converted into electricity.
But the engineering required to build one of these is just staggering. I mean, we are talking about machines that contain upwards of 300,000 individual parts.
It's incredibly complex.
In South Korea's Doosan Enerbility just signed contracts worth over 2 trillion won to supply 12 of these massive gas turbines to the U.S.
Which is huge.
But I want to dig into the why here. These machines have to endure temperatures over 1,500 degrees Celsius. At that temperature, standard metals don't just melt, they lose their structural integrity completely.
That is the core engineering hurdle. The turbine blades are spinning at thousands of revolutions per minute, while bathed in gases hotter than the melting point of the metal they are actually made from.
It's insane.
To prevent the turbine from vaporizing itself, you have to cast the blades from single crystal superalloys. You have to apply advanced ceramic thermal barrier coatings, and you have to engineer microscopic internal cooling channels where air flows through the blade itself.
It's like asking a precision watch to operate perfectly while submerged in a volcano for a decade.
Exactly.
So for decades, this level of metallurgy was an absolute monopoly held by just 4 companies globally, right? You had GE in the US, Siemens in Germany, Mitsubishi in Japan, and an Italian firm.
Yes, it was the absolute pinnacle of mechanical engineering, and it was highly guarded by those legacy players.
So if I'm an American tech giant, why am I turning away from a homegrown legacy company like GE and choosing a South Korean firm instead?
Well, it comes down to speed and execution. The legacy powerhouses are completely bogged down. If you order a turbine from GE or Siemens right now, you are looking at a 5 to 7 year wait list.
And big tech cannot wait 7 years.
No, the AI race will be decided long before then. Doosan offers much faster delivery timelines and highly competitive pricing because their manufacturing lines are just aggressively optimized.
Okay, so they beat them on speed and price. But if I'm Google, I'm probably worried about what happens when this Korean turbine breaks down in a data center in Texas.
Sure.
Do I have to halt operations and fly specialized engineers in from Seoul every time there's a maintenance issue?
You would think so, but Doosan actually anticipated that exact hesitation. They set up a dedicated subsidiary right in Houston, Texas.
Oh, wow. Smart.
So big tech gets the speed, the advanced materials science, and the pricing of a South Korean manufacturer, but with the immediate boots-on-the-ground maintenance of a local American contractor.
Okay, so gas turbines solve part of the problem, but they still require a constant physical supply of natural gas via pipelines.
Right.
What if a tech company wants to build a massive data center cluster in an area where piping in natural gas just isn't feasible? They need something incredibly powerful, but completely self-contained.
And that brings us to the next massive pivot. Small modular reactors, or SMRs.
SM.
Yeah. Traditional nuclear power plants are these sprawling complexes that take up the space of dozens of football fields. SMRs are roughly 1/100th the size.
Which is tiny in comparison.
You can theoretically transport the modules on the back of a specialized truck and just assemble them on site.
Which means you could plop an SMR right next to a hyperscale data center.
And, crucially, SMRs solve the agility problem. Traditional nuclear plants provide a massive, constant baseline of power. They are incredibly difficult to ramp up or down quickly.
Right, they just run at full capacity.
Exactly. SMRs, on the other hand, are designed to adjust their power output rapidly. When AI server loads spike during peak training hours, the SMR can ramp up output. When demand drops, it dials back.
Now wait, I have to play devil's advocate here for a second.
Go ahead.
When you look at the SMR landscape, the companies dominating the headlines are mostly American. Google is partnering with Kairos Power. Amazon is investing heavily in X-Energy. The pioneer in the space is NuScale. If all these U.S. companies are designing the tech, why are we giving South Korea the credit for American innovation?
That's a great question, because drawing up a brilliant next-generation reactor on a whiteboard in California is entirely different from physically forging it in the real world.
Okay.
The U.S. has zero commercial SMRs actually running today. Nuscale holds the brilliant designs, but the physical heart of the SMR,
The core?
yeah, the core reactor module that safely contains the nuclear reaction, is an absolute manufacturing nightmare.
So Nuscale isn't actually building their own reactors.
They can't. The U.S. has largely lost the specialized heavy forging capabilities required for this.
Why is that?
To build a nuclear core, you have to pour hundreds of tons of molten steel into a single massive ingot and then forge it so perfectly that there are zero microscopic imperfections.
Because if there is a flaw, the radiation and immense pressure will eventually exploit it.
Exactly. And the manufacturing for Nuscale's core reactor modules is being done by South Korea's Doosan Enerbility.
But doesn't that terrify the U.S. government? I mean, relying on a foreign nation to forge the physical core of American nuclear infrastructure feels like a massive national security vulnerability.
It definitely raises eyebrows.
Why would the U.S. just subsidize local steel mills to do it themselves?
Because industrial muscle memory isn't something you can just buy overnight with a government subsidy. The U.S. basically stopped building new nuclear plants for decades.
Right.
The highly specialized foundries closed down, the supply chains withered, and a whole generation of master metallurgists retired.
So the expertise is just gone.
Mostly, yes.
Yeah.
South Korea essentially positioned itself as the physical manufacturing foundry for America's SMR designs because they never stopped forging.
The intellectual property might be American, but the physical execution is entirely Korean.
Spot on.
And that actually explains the situation with large-scale nuclear power, too. SMRs are great for local agile power, but if you need to stabilize an entire regional grid that's collapsing under AI demand, you still need massive continuous baseload power.
And large nuclear is still king there.
Yeah. And the contrast in global capability here is really stark. Let's look at a recent geopolitical showdown from the sources.
Okay.
South Korea's Korea Hydro Nuclear Power, KHNP, recently won a massive 26.2 trillion won project to build 2 full-scale reactors in the Czech Republic.
Which was a huge win.
They beat out France's state-owned EDF, which is historically a global nuclear titan.
Right. And the reason why is clear. The traditional nuclear powers, the U.S., the U.K., France, they are completely bogged down in construction nightmares.
Look at the Vauxhall plant in the U.S. or Hinkley Point in the U.K.
Exactly. They are plagued by budget overruns that run into the billions and delays that stretch for decades.
But KHNP doesn't have that problem.
No, it comes back to continuous execution. When the U.S. tried to restart its nuclear program after a long hiatus, it was a disaster of inefficiency. They had to relearn how to coordinate these mega projects.
While South Korea just maintained a continuous, standardized build program for decades.
Yeah. Their APR 1400 reactor model is a perfect example. They took that model to the United Arab Emirates for the Baraka nuclear power plant project.
Oh, right.
They built 4 massive reactors in the middle of the desert over 12 years, and they did it on time and on budget.
Which is practically unheard of in modern mega infrastructure.
It really is. They can deliver world-class power plants 30 to 40% cheaper than American or French alternatives, with an actual guarantee that they will finish the job when they say they will.
Okay, so we've solved the generation side of the equation. South Korea is building the advanced gas turbines, they are forging the SMR cores, and they're constructing the large baseload nuclear plants.
Yes.
But there is a glaring logical gap here. Generating the power doesn't help if you can't physically move that electricity from the power plant to the data center.
Which brings us to the transmission grid. And as we established earlier, the U.S. grid is ancient.
Yeah, the average American power transformer is over 40 years old.
It's a massive bottleneck. You can have a brand new nuclear plant, but if you push that much power into a 40-year-old local grid, the transformers will literally blow up.
Relying on this grid for AI is like asking an old man to run a marathon.
That strain is exactly what is driving an unprecedented demand for ultra-high voltage technology. To move massive amounts of power efficiently, you need specialized high-capacity transformers.
And historically, Chinese firms provided a lot of global electrical equipment, but they are currently locked out of the U.S. market due to geopolitical tensions and tariffs.
Leaving the door wide open for South Korea, companies like HD Hyundai Electric, Hyosung Heavy Industries, and LS Electric are just sweeping the board right now.
The numbers are wild. HD Hyundai Electric now holds the #1 market share in the U.S. for ultra-high voltage transformers.
Literally 1 in every 5 new transformers being installed across the American grid is made by them.
And Hyosung just locked in a record $780 billion deal with a single U.S. grid operator.
But it's not just the transformers stepping up the voltage, it's the actual cables carrying the current.
Right, high voltage direct current, or HVDC cables.
This is a critical technological shift. Traditional grids use alternating current, or AC, but think of an AC grid like a local road network with a traffic light at every intersection.
Okay.
Every time the power stops or switches, it loses energy as heat. When you are transmitting massive loads of power over very long distances, say, from a remote nuclear plant to a data center hub miles away, AC is terribly inefficient.
So HVDC is like building a sealed, direct superhighway with no off-ramps.
Precisely. The power just travels in one direction instantly, with almost no energy loss as heat.
And LS Cable, another Korean firm, is sitting on a $7.6 billion backlog for these specific HVDC cables.
They're literally manufacturing the central nervous system of the new AI grid.
Let's pull the lens back even further. We've got the power plants generating the juice. We've got the ultra-high voltage superhighways moving it.
Yeah.
But I want to go back to those gas turbines for a second. What actually fuels them? Because if the U.S. is building these turbines to power data centers, they need a massive supply of natural gas.
They need liquid natural gas, or LNG. The U.S. happens to be the world's top exporter of LNG. They have the fuel.
But transporting it across oceans or coastlines is an absolute nightmare from a material science perspective.
Oh, totally. Because you can't just pump raw gas into a regular cargo ship. To transport it efficiently, you have to supercool the natural gas until it condenses into a liquid.
Which requires dropping the temperature to negative 162 degrees Celsius.
And at negative 162 degrees Celsius, regular maritime steel becomes incredibly brittle. It will literally shatter like glass if a wave hits the hull.
That sounds terrifying. So how do you actually build a ship that can hold a lake of freezing liquid without shattering?
You have to line the massive cargo tanks with specialized Invar alloys. It's a nickel-iron alloy that barely expands or contracts with extreme temperature changes.
Okay.
You have to build complex membrane containment systems and layer them with advanced cryogenic insulation. Welding these alloys is notoriously difficult. The margins for error are microscopic.
These ships are essentially giant, highly volatile thermoses floating on the ocean.
They really are.
And it turns out the U.S. completely lacks the maritime industrial base to build them. So who builds them? South Korea's big three shipbuilders.
HD Hyundai, Hanwha Ocean, and Samsung Heavy.
Together, those three companies command 70 to 80% of the entire global market for LNG carriers.
The U.S. might have the natural gas, but they are entirely dependent on South Korean shipyards to actually move it. We're seeing American energy giants like Cheniere Energy handing over billions in recent orders straight to Korean shipbuilders.
When you lay it all out like this, it is almost unbelievable. South Korea holds the entire infrastructure stack.
They really do.
They build the cryogenic ships to transport the fuel, they build the high-temp turbines and nuclear reactors to burn the fuel, and they supply the heavy-duty transformers and HVDC cables to move the electricity.
It's the full package.
How does one country, roughly the size of Indiana, dominate so many extreme heavy industrial sectors simultaneously?
Well, it wasn't an overnight AI miracle. What we are seeing today is the dividend of decades of sheer, stubborn manufacturing grit.
Yeah.
While most Western nations shifted their economic focus toward digital services, finance, and software design in the 90s and 2000s, South Korea made a cultural and economic commitment to heavy industry.
They just never stopped pouring concrete, forging steel, and welding ships.
Exactly.
I was reading through some of the historical context in the sources, and the anecdotes of how they built this industrial base are just incredible. Look at the origin of their shipbuilding dominance.
The Hyundai story.
Yes. In 1973, Chung Ju-young, the founder of Hyundai, wanted to build a massive shipyard, but he didn't even have a dry dock. He just had a picture of an empty beach.
It's wild.
And he flew to London to meet with executives at Barclays to ask for a massive loan.
The audacity of that meeting is legendary. The British bankers were highly skeptical. Why would they lend millions to a country with no modern shipbuilding history?
Right. And Chung Ju-young reaches into his pocket, pulls out a 501 coin, and slams it on the boardroom table.
So good.
On the back of the coin is an image of a 16th century Korean ironclad turtle ship. He looks at the bankers and says, "We have been building ironclad ships since the 1500s, 300 years before the British."
He used a piece of pocket change to brute force British capital into funding Korean industry.
It's a perfect illustration of their willpower.
And you see that same grit in their nuclear program. In the 1980s, the South Korean engineers partnered with American firms to learn nuclear technology.
Right.
But the Americans treated them as junior apprentices, keeping the core engineering secrets heavily guarded. So the Korean engineers would stay up all night, tracing and copying complex American blueprints by hand, reverse engineering the math just to understand the underlying principles.
They literally hand-copied their way into becoming nuclear savants.
They did.
And it didn't stop in the 80s. When Doosan decided they wanted to build their own indigenous gas turbine in 2013, the legacy players mocked them. The industry consensus was, you think you could just wake up and build a 1,500-degree turbine from scratch?
But they endured the mockery. They spent 12 grueling years partnering with hundreds of local small businesses and universities.
Wow.
They failed, they iterated, and they refused to give up until they successfully fired up a world-class turbine. They kept digging deep into heavy, dirty, physical manufacturing, while the West was obsessed with creating the next social media app.
And now we have this beautiful irony. The infinite, weightless, purely digital world of AI.
The algorithms, the cloud.
Yeah, the large language models. None of it can survive without the massive, physical, sweat and steel infrastructure that South Korea perfected.
Big tech assumed the future was entirely in the cloud. They forgot that the cloud actually runs on massive amounts of concrete, specialized alloys, and gigawatts of electricity. It is the ultimate revenge of the physical world.
So to summarize this incredible pivot, South Korea has quietly executed one of the most brilliant strategic maneuvers in modern economic history.
Truly.
Everyone knows them as the memory chip capital of the world, supplying the HBM chips that go inside the GPUs. But they're not just selling the silicon anymore. They offer the total full package for AI energy infrastructure.
They have positioned themselves as the irreplaceable physical foundation of the global AI race. Without their cryogenic ships, their heat-resistant turbines, their forged reactors, and their superhighway cables, the American AI dream simply grinds to a halt.
It really changes how you look at the technology we use every day. The next time you open up an AI tool and you type in a prompt and it spits out a brilliant answer in 3 seconds, I want you to picture the massive physical and industrial supply chain making that happen.
Yeah, picture the supercooled LNG ships crossing the ocean.
The 1,500-degree gas turbines spinning at thousands of RPMs.
The ultra-high voltage cables stretching across the desert.
That single prompt is being powered by a colossal symphony of heavy industry.
And this raises a fundamental question, something I think you should ponder as this AI arms race accelerates. We always assume the future belongs to the coders.
Right?
But if the limitless, purely digital future of artificial intelligence is completely chained to the hard realities of heavy industry, of forging flawless steel and pouring reliable concrete,
Yeah.
does true global supremacy actually belong to the countries with the most advanced algorithms, or the ones who never forgot how to build the physical world?